Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 54 on Power Series.
At last, we've assembled all the tools we need to adequately and accurately describe how, when, and in what manner infinite series converge. In this lesson, we're going to apply these tools to power series.
In this chapter, and indeed in this course, we've seen several instances of turning functions into sequences through some sampling process. We now turn to the problem of reversing that machine, of converting sequences into functions. One mechanism for doing so is the power series. A power series in X is simply a series that has the variable x inside of it as a monomial term, something of the form sum n goes from 0 to infinity of a sub n, x to the n, where now a sub n is considered a coefficient. We're going to think of the notion of a power series as a machine or an operator that converts a sequence, a sub n, into a function, f of x. Let's begin with some simple examples. If we have a sequence, all of whose terms are 0, except for 1 in the nth slot, then the power series is simply the monomial x to the n. Now, if we have a finite sequence in the sense that only finitely many of the terms are non-zero, then this will have a power series that is a sum of monomials with coefficients in front of them that eventually terminates. We call that a polynomial. Now, if we have something that does not eventually end in zeros, we're going to have to be a bit more careful, but this isn't so mysterious. If we have the sequence of all ones, we recognize that the power series for that sequence is simply the geometric series. And this gives us the function 1 over 1 minus x, at least when x is less than 1 in absolute value. Other sequences can be easily seen to correspond to interesting functions, though one may have to do a bit of algebra to see it. If we look at certain sequences, we'll recognize some old friends, log of 1 plus x, or e to the x. These correspond to certain power series. Now, what if we have a sequence that does not go to 0, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc.? Will that converge to anything? Well, of course, this isn't so bad. This one corresponds to the function 1 over quantity 1 plus x squared, as you can see from squaring the geometric series. In fact, we can have sequences that grow rather large, but which have power series that converge to something very simple. Now, what if we just take any old interesting sequence of coefficients? What will that converge to? Sometimes it's a bit of a mystery. Let's look at the Fibonacci sequence and let us denote by script f the power series whose coefficients are f sub n, the terms in the Fibonacci sequence. Now, if we were to multiply this power series by x, what would happen? It would give us a new power series associated to a shift, a right shift of the Fibonacci sequence. If we were to do it again, then we would shift over to the right yet once more. And the reason for doing this is to line up the coefficients to match the recursion relation that the Fibonacci sequence satisfies. Fn plus 2 equals Fn plus 1 plus Fn. Now, if we take a look at the coefficients in front of the monomial term, x to the n, for these three power series that we have written down, then we see from the recursion relation the relationship between them. The first is the sum of the latter two. And so if we were to subtract x times script f and x squared times script f from script f, what would we obtain? Most of the coefficients of the monomial terms are 0 because of the recursion relation. When we add up these power series, the only thing that is non-zero is in the constant term, where we get f naught, and the first order term, where we get f1x minus f naught x. Now, because we know the exact values of f naught and f1, we see that on the left we have f minus xf minus x squared f. On the right we have simply x. Solving for script f gives us the power series formula that script f, the power series, the Fibonacci sequence, is equal to x over 1 minus x squared. Now, that's what it is, but what does it mean? What do we do with this? These functions that generate the power series have within them all sorts of interesting questions. They tie together recursive properties, enumerative properties, approximation properties, and convergence. We're going to focus on issues of convergence. Consider a power series f of x, the sum of a sub n, x to the n. The following theorem holds. For some capital R between 0 and infinity, perhaps achieving either of those values, f of x has the following convergence behavior. It converges absolutely if x is less than r in absolute value. It diverges if x is bigger than r in absolute value. Now, this r is a very special number associated to the power series. It's called the radius of convergence. Let's see, how would we prove this theorem? What tool would we turn to determine convergence? Well, let's start with our friend, the ratio test. Here, what we need to do is compute rho, the limit as n goes to infinity, of the ratio of the n plus first term to the nth term. Now, what are the terms? Well, here they are a sub n times x to the n. So taking the ratio of incident terms will tell us what we need. Now, we have to be careful to take the absolute values, since the ratio test requires a positive sequence. Okay, so doing that, what do we see? We get some cancellation with the x's, and we can rewrite this as the limit as n goes to infinity of the absolute value of a sub n plus 1 over the absolute value of a sub n times the absolute value of x. Now, if that is less than 1, we have absolute convergence. If that is bigger than 1, we have divergence. So, where is this capital R coming from? Well, it is precisely the reciprocal of this limiting coefficient, since if we divide by this on both sides, we get the appropriate answer. When rho is less than 1, that's the same thing as saying that x is strictly less than r in absolute value. That means we have absolute convergence. When rho is bigger than 1, that's the same thing as saying x is greater than r in absolute value, and that means divergence. So what matters is this radius of convergence, capital R, the limit as n goes to infinity of absolute a sub n over a sub n plus 1. Be sure to remember that, and be sure to remember that it's the nth term over the n plus first term, not the other way. Now, this radius of convergence is called a radius of convergence because it's telling you the distance away from 0 past which your power series is going to diverge. But within that, you're fine. Now, you do have to be careful. We said nothing about the endpoints of the domain because, of course, the ratio test tells us nothing in that case. So you're going to have to be careful and check explicitly at those endpoints. Let's see a simple example. If we consider f of x, the sum over n, negative 1 to the n, square root of n, quantity 2x to the n, then our coefficient a sub n is negative 1 to the n, square root of n, 2 to the n. To compute the radius of convergence, we take the limit of the a sub n divided by a sub n plus 1, all in absolute value. That gives us the limit as n goes to infinity of square root of n, 2 to the n, over square root of n plus 1, 2 to the n plus 1. That is, as you can easily see, 1/2. Therefore, within 1/2 of 0, we have absolute convergence. Outside of that, we have divergence. What happens at the endpoints? Well, we need to check what happens at x equals negative 1/2. If we plug in a value of negative 1/2 in for x, what do we get? We get the sum over n of square root of n, since the negative 1 to the n's cancel. That is a divergent series. So at the left-hand endpoint, we have divergence. At the right-hand endpoint, at x equals 1/2, you can easily see that we get the same sort of series. That, too, is going to diverge by the nth term test. Now, other series that we've seen throughout this course have similar behavior. If we look at the geometric series, this is the power series where all the coefficients are equal to 1. The radius of convergence, in this case, equals 1, and this diverges at both endpoints, at plus and minus 1. If, on the other hand, we consider the power series with coefficient 1 over n, as n goes from 1 to infinity, then what do we see? This, too, has a radius of convergence equal to 1. And at the right-hand endpoint, we obtain the harmonic series, which certainly diverges. But at the left-hand endpoint, at x equals negative 1, we get the alternating harmonic series. That converges, but it does so conditionally, not absolutely. If we consider the power series x to the n over n squared, where the coefficient is 1 over n squared, this also has radius of convergence equal to 1, but it converges at both endpoints and does so, therefore, absolutely. Some power series come to us in a slightly different form, that of a shifted power series, something of the form sum over n of a sub n times quantity x minus c to the nth. This, of course, is just a power series shifted over by c units. In this case, if we compute the exact same radius of convergence, then what we will find is that this shifted power series converges when x minus c is less than r in absolute value. That is, when x is within r of c. R is thus a distance to the center, c, of the shifted power series. For an example of a shifted power series, consider the sum of 3x minus 2 to the n over n times 4 to the n. Now, this is not in the form of x minus c to the n, so we're going to have to do a little bit of algebra to get it into that form. But I claim that by factoring out a 3/4 to the n and absorbing that 3 to the n term from the denominator into the numerator, we get the equivalent sum of 1 over n times 3/4 to the n times x minus 2/3 to the n. That means that this shifted power series is centered at x equals 2/3. Now, to determine the radius of convergence, we isolate the coefficient a sub n as 1/n times 3/4 to the n. We compute the radius, r, as the limit as n goes to infinity of a sub n over a sub n plus 1. That yields, after some algebra, the limit of n plus 1 over n times 4/3, which is precisely 4/3. Therefore, the domain of absolute convergence is all x within 4/3 of 2/3 the center. Now, what happens at the boundary points? Well, on the left, we have x equals negative 2/3. That is 2/3 minus 4/3. Substituting in x equals negative 2/3, we obtain, after a little bit of cancellation, the alternating harmonic series. That, of course, converges. When we substitute in the right-hand endpoint, that is, x equals 2/3 plus 4/3, or 2, then we obtain, substituting in, a series which is the harmonic series. This, of course, diverges, so that we have conditional convergence on the left, divergence on the right.
In our next lesson, we're going to focus attention on a particular type of power series obtained from a smooth function f of x. Perhaps you've heard of these. They're called Taylor series.